All right. In this video, we are going to go over the last pieces of information you need for the final exam. These questions will be on the final, most likely, but it'll only be a few. And they're relatively easy questions to get the concept of, that is, but let's go over them. So we have learned different ways to tell if a reaction is spontaneous. Right? So delta G, if that's negative, that's spontaneous. Ecell, if that's positive, that's spontaneous. K, E, Q are equilibrium constant. If that's greater than 1, that's spontaneous. And all of these are just different ways we can measure delta S universe. Remember, if delta S universe is positive, that means it's spontaneous. So since these are all three of these are measuring the same thing, we can convert between all three. And we've already done that for delta G equals minus RT ln of KEQ. So that's how we convert between K and delta G. But the next thing we're going to learn is how to convert between delta G and E cell. Delta G naught, that should have been not, equals minus NF E cell. So N is the number of electrons moving in the reaction. So remember, when we do E cell calculations, that's a redox reaction. So we're looking at the number of electrons are moving. E cell, right? We already calculated that, right? That's your cathode minus your anode. And F, we have actually used before already. That is Faraday's constant. And that is there are 96,485 coulombs for every 1 mole of electrons. All right, so that is the pieces of information we need to know for converting delta G and E cell. So let's actually look at a problem. So we have PB 2 plus aqueous plus MgS. So Mg solid goes to PB solid plus Mg2 plus aqueous. And the reduction potentials, so lead plus 2 electrons goes to lead solid. That has a reduction potential of negative 0.13 volts. And magnesium has a reduction potential of negative 2.37 volts. And the question is, what is delta G naught for this reaction? So for any E cell reaction, the first thing we want to do is determine what's the anode and what's the cathode. So lead went from +2 to 0. So if I'm going to +2 to 0, I gain electrons, which means I'm reduced, which means I'm the cathode. Magnesium went from 0 to +2. So I became more positive. That means I lost electrons. That means I was oxidized, and so I'm the anode. So the first thing we want to do is calculate E cell for this reaction, which again is the reduction potential of the cathode, so negative 0.13 volts, minus the reduction potential of the anode, negative 2.37. So negative 0.13 minus a minus 2.37 is 2.24 volts. All right, so that's E cell. Now we have to do the number of electrons that are moving, N. So lead went from +2 to 0, so that's a change of 2 electrons. Magnesium went from 0 to +2, so that's also a change of 2 electrons. So N is simply 2. And this is often confusing for people. You might want to say, well, there's 2 electrons moving each time, so shouldn't that be 4? What is really going on is that the magnesium is giving the 2 electrons to the lead, right? So that's why we see a change of 2 each time. And I'll show you another case in a minute where it's a little more difficult to tell, but I'll show you how to do that. But let's finish this problem. So we have N, we have Ecell. Faraday is 96,485 coulombs per mole of electron. So we have everything we need to do. So it's delta G naught equals minus number of electrons times Faraday times our Ecell. So this is equal to -2 times 96,485 times 2.24. So our voltages, let me calculate this. Sorry, just getting on my calculator. 2 times 96,485 times 2.24. 432,253, and this will have the units of joules per mole. Right, so that's an easy calculation to do once you find out the number of electrons. Now, let's say that we had another reaction. This time, I'm going to change the charges. Let's say lead was actually 3 plus magnesium, and magnesium solid. That goes to magnesium 2 plus lead solid. So the question here is, what is N? And here, if you were to do the same thing we just did, you would see lead gained 3 electrons, magnesium lost 2. Now, the trick is when you have this happening, that is where you don't have the same number of electrons moving between each molecule, we have to be aware that when we are balancing reactions, the charge has to be the same on each side. So right now, my charges are, I have +3 on my reactants and +2 on my products. That's unbalanced, right? And so I'm going to make each of these +6. And I choose +6 because 3 times 2 is 6. So that's the easiest thing to do when you have charge and balance. Multiply your 2 charges, and that's going to show you what you need to get to. So let's get to 6. So if I make 3 magnesiums over here, then I become +6. However, from balancing reactions, if I have 3 magnesiums as my products, I need 3 magnesiums as my reactant. Having 3 magnesiums as my reactant doesn't change anything because my charge is still 0. Now I'm going to do lead, something similar. I'm going to add 2 lead 3 plus and 2 lead 0. That makes +6 over here. So now we have a balanced reaction, and we see if we were given this reaction, N would be 6. I'm moving 6 electrons. All right, so that's all I have to tell you about Ecell. And the last topic we are going to talk about is nuclear chemistry. All right, so this is a field that only started about 100 years ago with the splitting of the atom. And the thing about nuclear chemistry is that it changes the rules of chemistry. And what I mean by that is all throughout Gen Chem, we always said, you know, for example, if I have A plus B interacting, on the other side of my reaction, I have to have the same molecules. I can't create or destroy atoms. Well, nuclear chemistry says you can definitely do that. Nuclear chemistry is the process of creating or destroying atoms. So first off, let's just talk about our notation here. Whenever I do nuclear chemistry, I'm going to write my elements like this. So X is the symbol, and that's just from the periodic table. For example, carbon is C, nitrogen is N, oxygen is O. So we're used to that. Z is the atomic number, which is just the number of protons. You can find this easily on the periodic table. For example, carbon has an atomic number of 6, nitrogen has 7, oxygen has 8. Those are the number of protons, and those are the element numbers in the periodic table. A is the mass number. It's how many protons you have plus how many neutrons you have. So if the atomic number is the number of protons, you can figure out the number of neutrons just by subtracting the two. And during a chemical reaction, well, a nuclear reaction, rather, we call the atom that is our reactant the parent nucleid. We call the element that is our product the daughter nucleid. All right, and for nuclear chemistry, there's only a few reactions we need to know. So let's go over our new reactions. The first is called an alpha decay. So first off, what is alpha? So an alpha, they're often called alpha particles. And all that is a helium atom. It's a helium atom with two neutrons. So helium has two protons and two neutrons. So if we look at the alpha decay of uranium-238, so uranium, if you look on the periodic table, it's element 92. In an alpha decay, one of our products will be helium-42, and our daughter nucleid would be, well, let's see how we do this. So for nuclear chemistry, the trick is the top number has to be the same on both sides of the equation. So I have 238 on the left, and if I have 4 on the right, I have to have 234. For my bottom number, if I have 92 on the left, I have 2 here, and I'll have 90 there. So 2 plus 90 is 92. Now I have to tell what element this is. So I have to look on the periodic table and find element number 90, and that'll be TH. So TH 234 is my daughter nucleid. So that's an alpha decay. You are making a helium-42. How about a beta decay? All right, so what's a beta particle? A beta particle is just an electron. So it's an E0 minus 1. So let's look at radon 228 as our example here. So if I'm going through a beta decay, I'm going to make an E0 minus 1. Now, following our rules of nuclear chemistry, my top number, my protons and neutrons have to be the same number. So I'm going to make a 228. And then my number of protons has to be the same. So I have 88 on the left, a minus 1 on the right. So that has to be an 89. I look on the periodic table, find out what element 89 is, and that is AC. So that's a beta decay. You are losing an electron. How about a positron emission? So what's a positron? A positron is basically a positively charged electron. So E0 plus 1. Let's go phosphorus 3015 as our parent nucleid. If I'm doing a positron emission, one of my products is E0 plus 1. Now to find my other product. Well, 0 plus 30 is 30, so I need 30 as my mass number. My atomic number has to equal 15. I already have 1 over here, so that'll be 14. Looking up element 14 on the periodic table, that is silicon. So that's silicon 30. All right, the last type of reaction is the electron capture. So this one is different in that you're going to have a new reactant. And our reactant, as given by the name, is an electron. So here, let's do Ru92. And if this is an electron capture, that means I get a new reactant. But it's the same rule. So 92 on the right because I have 0 for my electron. And I'm also going to be element 45, 44 minus 1. Or sorry, I don't know how to do math. 44 minus 1 is 43. That's TC. So those are the four types of reactions we will see in nuclear chemistry. An alpha decay, which you spit out a helium-4 a beta decay, which you spit out an electron, a positron emission, where you spit out a positively charged electron, and electron capture, which you capture an electron. Now, the last thing we are going to talk about is the kinetics of radioactive decay. So things that are radioactive will break down through our different decays, like an alpha decay and a beta decay. And these follow the kinetics of a first order half-life. Let's remember our terminology. We talked about this in the kinetics chapter. So let's say I have, radioactive uranium that's going through decay. I have 100% of that to start. And the time it takes for me to go to 50% of that, that is our half-life time. Right? How long it takes to go to 50% of my starting material. So what I've shown you so far is one half-life. Then if I go to uranium 25% of my 50, that is a second half-life. And it's the same time. So for a half-life reaction, T1/2, that is equal to 0.693 divided by K. So if I want to have my half-life time, I need to take 0.693 divided by K. All right, let's talk about K. We've talked about a lot of different Ks this term, but this K is not an equilibrium constant. It's a rate constant. So if you remember during the kinetics chapter, we had problems where we said A goes to B with a rate constant of K1, B goes back to A with a rate constant of K-1. That's what this K is. It's a rate constant. So it's just a number, a constant for every different reaction, right? So if we know the half-life time, we can find K. If we know K, I can find the half-life time. And then we can take this reaction or this equation and have another equation with it. So the equation I just wrote down, natural log of NT divided by N0 equals minus KT. This allows us to know how much stuff at time t divided by how much stuff at time 0 equals minus K. So that's a K we just found. And T is time. So what the equation I just wrote down allows me to do, a couple things. It allows me to calculate how long it will take for my material to break down to a certain percentage. Or I can say, after so much time, how much percentage of stuff will I have left over? And let's do a problem to figure this out. So this will be problem 121. This problem says U-235, which is spent nuclear fuel, goes through alpha decay with a half-life of 703 million years. And the question is, how long will it take to be left with 10% of U-235? So how long will it take to break down till we only have 10% of it left? So the first thing we need to do is figure out K. So T1/2 equals 0.693 divided by K. I can take this equation and rearrange it to say, well, K is actually 0.693 divided by T1/2. And we know what T1/2 is. It's given in our reaction. So our half-life time is 703 with a unit of million years. So I'm going to keep that as million years. So let's do this. 0.693 divided by 703. So my K is 9.86 times 10 to the 1, 2, 3 times 10 to the minus 4. And it has a unit of 1 over millions of years. So that's how I find my K. And now we can actually answer the question, how long will it take? Remember, our equation is natural log of nt divided by n0 equals minus kt. And we're solving for t here. So n0, we need to come up with an initial amount. And the thing about first order, it doesn't actually matter how much you start with. It will all go the same speed. So let's just say we start with 1 uranium. And so 10% of 1 is 0.1. So if I start with 1, I'm going to 10% of that, which is 0.1. So let me do the natural log of this. So the natural log of 0.1 is negative 2.30. And I'm going to divide that by my negative k, which is 9.86 times 10 to the minus 4. That equals time. And so my answer is the time it takes for this uranium to break down to 10% of what it started with is 2335 with a unit of millions of years, or 2.3 billion years. So all the radioactive material we're making right now, the waste product will be around for another at least 2 billion years. But yeah, that is our last piece of information, how to do half-lives of radioactive decay. So if you have any questions about this topic or anything else, be sure to let me know. Otherwise, study hard on the final, go over the problems we did in class, look at our notes, and you should have, and nothing should really seem unfamiliar. We have covered the vast majority of the questions you will be looking at. But yeah, just let me know if you need help. Otherwise, I will see you at the final. Have a good one, everyone.